Okay, we continue with part 2 of the so let's say part 2. Continue manipulating the equation related to Mohr circle as we got it. So here let's number these equations. So let's call it 1, 2, and 3. So I will manipulate 1 first such that I bring s prime x, the first term, on the right hand side to the left hand side. And square it. So this will give me sx minus sy divided by 2 square cosine 2 theta square plus sxy sine 2 theta square plus 2 times this term times this term. So I will get 2 times sxy times sx minus sy divided by 2 cosine 2 theta times sine 2 theta. Now I come and manipulate equation 2 by just simply square it. This becomes square, so minus will go away. And the square of the second term. And minus, because there's a minus 2 times sxy sx minus sy divided by 2 cosine 2 theta sine 2 theta. Now let's sum up these two expressions. Summation give me on the left hand side s prime x minus sx plus sy divided by 2, the whole thing square, plus the left hand side of the equation 2, and look what happens to the right hand side. This term and this term, if I factor out x minus x sy divided by 2 square, sine 2 cosine 2 square becomes 1. Therefore, I will get sx minus sy divided by 2 square. Similarly, for this term and this term, I will get sxy square. Because if you factor out there's a square missing here, sxy squared, then sine 2 plus cosine 2 theta both square becomes 1. So this is taken care of. And these two simply cancel out. So this is what I get. And that is a profound conclusion. That is basically an equation of a circle if I define coordinates, let's say sigma for normal and tau for shear, and take this as my center and take this as my r square. In other words, the center is on sigma axis at Sx plus Sy, which is the average of the normal stresses from the origin. Yeah, from this origin you get a point C. And this is the center of a circle. The radius is Sx minus Sy divided by 2 square plus Sxy square. So basically we come here and calculate the average stresses. I sketch it, but I will draw it more neatly with some tools and draw a circle. And this circle has the radius of r, which is this value here, which we can calculate. Now, this circle is based on a given initial state of stress that we initially identify here. Sx, Sy, tau xy. So we need 3 numbers to build this. Once built, then any point on this circle represent the rotation of the initial stress components. In other words, if you rotate your coordinates by any theta, any angle, then this circle will represent that. Noting that a rotation of 2 theta on this Mohr circle is actually the rotation of theta in actual physical world. Why is that? Because of these 2 theta that we had. So the mathematics indicates that we should write it in 2 theta, and then once we do that, we get the equation of a circle. We don't get the equation of a circle here in theta, but we get it in 2 theta. That's a very neat point about Mohr circle. But sometimes it's confusing. I will remove this confusion using Paul method later, but this is what it is. So at this point, I have an equation of a circle, and once it is written, then it is good. Let me point out a few points here that is very important. These 2 points that actually this circle crosses the sigma axis, these are principal stresses. What does it mean? It means that at this orientation, the normal stresses are maximum. This is a very useful information. And shear stress is 0. Whereas at this location, tau is max. Shear stress is max. So at this orientation, let's say you start from a point, initial point, say here, and then if you rotate this way, this much, then you will get to the principal stress. If you rotate to this direction, you get to the maximum shear stress. But at maximum shear stress, we will have some normal stresses. Most of the cases, it is possible that you don't have it, but in many cases we have, because the center doesn't coincide with the origin necessarily. But definitely at principal stresses, we will have no shear. So immediately we can identify these 3 important points, and then have a good visualization about the principal and principal direction. Direction is the amount that you have to rotate. Of course, here, if you measure it from center, it's 2 theta, but actual theta in the physical world. So I will do an example and explain these details. But the main point that I want to bring it here in part 2 is this connection to the mathematics and why we have a circle. Why do we have a Mohr circle? Why we don't have a Mohr ellipse? because this equation, after it is written into theta, it is exactly an equation of a circle with defined center and radius, as we discussed here. To demonstrate this variation, I built an Excel sheet that you see here on the screen. On the left hand side here for data, you see the Sx, Sy, and tau xy, and give it the numerical value. So I have a normal stress of 150 units, whatever is the unit, could be megapascal, pascal, psi, whatever is the unit. And tau, the shear stress on that plane. Remember that these are the plane that we discuss here. And I will take this plane as a reference. I will take this plane as a reference. Let me make it red here. So this is the plane that usually we take it as a reference. Any plane can be a reference, but traditionally, usually we get this plane, which is basically the plane which is perpendicular to the x-axis with the unit normal in the direction of the x-axis. But you should feel free to take any other plane. So we basically, when we rotate, we would like to have a reference point. So in this Mohr circle, you have to do three things. I have explained this so far and the equation, and there is a sign convention about the tau shear stress that I will explain as we move forward. Okay, so this is clockwise. So basically, it is downward in the clockwise direction on that surface that I mentioned, normal to the x, in red color. And then Sy is a compression of 40, minus 40 in terms of the stress. Now, I listed some values for theta from 0 to 90 degrees and calculated the Sx prime, tau x prime. I mean, I mentioned y prime because it's the same as prime. I didn't prime on the coordinates. Basically, it's the same as S prime x. So if you want to have the equation is basically the equation that we have just derived. This equation. And simply for the others, we use these equations. So tau x prime and all of them. Now, so simply for this list of theta, calculate these stresses, and the graph shows the variation. For example, if you start rotating your element, the increment is 10 degrees here. So basically 5 degrees, if I go 10 degrees, I go to 180 basically. So for S prime, so as you see here, as you rotate from 0, the stress will go up and then comes down, gets a minimum, and then repeats itself. The shear stress, the red line, is similar. It will go downward, get a minimum actually, and then a maximum. One point here is that exactly it is not shown here, but we can calculate and we will discuss it. That at a maximum point, which is the normal stress and it is principal stress, if you come down, the shear stress 0. So if you go here, the shear stress 0 based on approximation of the cursor location is at 20 degree and the shear is minus 2276. And then if you go here at 20, your shear is 159.9 which is one of the principal stress. And the corresponding is also true for the minimum. The shear stress is zero and maximum normal stress is minimum. And this is the stress on the surface perpendicular to what we kind of take it as a reference on this surface. Maybe I shouldn't change the color here. This surface. Okay. And this is a possibility that you can build a spreadsheet and then see clearly the variation of these things. You may say, why do I need Mohr circle? Well, in principle, you're right. You don't need it per se, but Mohr circle is beautiful because it has a visual characteristic to it, and quickly you see how things happening. And this is the next part that I will go through. But up to here, for a two-dimensional stress transformation, plane stress, shall we say, this is all you need, and then you can play with it. There are some special cases that I will discuss later. Otherwise, we can say that this completes the discussion of plane stresses. Before ending this part, or maybe quickly going to construction of a Mohr circle, I would like to also show you I would like also to show you an app that I built. And this app, if I come back here, and give it the same values, 150 for sigma x and sigma y minus 40 and tau xy 50 plus, because it is clockwise positive, then we will see that this app is, I check the app and the values are good. I use one of the AI tools to, after several iterations, to build this. And then this is my construction and instructions, just supported by AI tool for programming, for coding as a HTML file. So you see that for these values, I get the average 55, sigma 1 is 162, 52 sigma 2, tau max, we saw that. And then if you look at this here, for any point that you have on the circle, you can also manipulate this. So if I come on this point, it is 0 orientation. And then if I rotate, let's say clockwise, to come to my sigma 1, see that sigma 1, my rotation is 14 degrees. So that's what I was saying. If you want to rotate your element, you should rotate your element by 14 degrees physical. Here is 28 actually, if you measure. At 14 degrees, if I rotate this element and ignore this element, it's a little bit messy. Need some more work to fix it. But if you rotate this element, your shear stresses will disappear on the sides, and only you will get normal stresses. Okay, so that should do it. So if I come back to our original slide or writings, we have done this there, and then also equation and how does it relate to a Mohr circle. So next video I would like to actually use a tool called GeoGebra to construct the Mohr circle and lead you to three-dimensional stresses and maybe some special cases for Mohr circle. So I keep this second video a little bit short. Maybe we have the third one as more lengthy one because we have to deal with construction and also the three-dimensional stress transformation using analytical methods, which is eigenvalue and eigenvector. Thank you.